Hey class, today we're going to continue on with chapter 4 and we're going to start section 4.2 known as the structure of the nuclear atom. Now a lot of the stuff we're going to talk about today is going to sound familiar because you have learned it in integrated science. However, today we're going to go into a little bit more depth and maybe some of the experiments we're going to talk about. So this section is actually going to be cut into two parts and we're going to cover part 1 today. And we're going to start off by going into and continuing from section 1, and we're going to talk about Dalton's atomic theory again. We covered those 4 postulates yesterday, or in the last class period, and we know that much of Dalton's atomic theory is accepted today. However, there were a few parts that I said were incorrect, and one of those parts, or the most important change, was we know that atoms are now known to be divisible, which means you can break them down. In fact, they can be broken down into smaller particles known as subatomic particles. So what exactly are subatomic particles and what are the 3 kinds of them? Well, hopefully from last year and even junior high, you remember that the 3 kinds of subatomic particles are the electrons, protons, and neutrons. And we're going to talk about each one of those separately, and we're going to talk about the experiments that led to know different things about these subatomic particles. So the first one we're going to talk about is electrons. So in 1897, an English physicist named J.J. Thompson discovered an electron during his cathode ray experiment. And if we don't know what an electron is, we have defined it down below. It is a negatively charged subatomic particle, so negatively charged. One of the major things people want to know from this section, since we cover so much about the experiment, is I'm going to tell you right now, I care about which scientists did what experiment and what they discovered. Not necessarily how they did it, just the name of their experiment and what they discovered. So for example, in your test, I would know J.J. Thompson discovered the cathode ray experiment. So Thompson performed experiments that involved passing an electric current through gases at low pressure, and he sealed the gases in a gas tube, and I'm going to show you a picture of the tube in the next couple slides. And at each end, he put a metal disc called electrodes. And those electrodes, he hooked them up into a source of electricity so that electricity flew from one electrode to the other. So here is a good picture of his experiment. Again, here he has a sealed tube. He's passing electricity through that, or an electron way. And then here is one electrode on one end, and here is another on the other end. Now, the way his electrodes work is one was called an anode, and it was positively charged. The other was the cathode, and it was negatively charged. So over here, that's why you see this negative and this positive. So electrons flowed from one side to the other, and right now we have a straight line. So the beam of electrons was known as a cathode ray, hence the name cathode ray experiment. Then, instead of having a straight line, he wanted to see what happened if he put a plate on either side. So here he put a positive plate on the top. Here he put a negative plate on the bottom, and he wanted to see how did that affect his cathode ray. And we're going to see that when he put a positive plate on top and a negative plate on bottom, that it deflected the ray, or it caused the ray to bend. And the reason it did this is actually a good phenomenon that helped him decide what that ray was made up of. So a positively charged plate actually attracted the cathode, and the negatively charged repelled it. So this is a very important sentence right here. Now, what does that mean in terms of science, and how did he know that was a negative electrons? Well, he knew a little bit of background information. Thompson knew that opposite charges attract. So positive and negatives attract. And he knew that like charges, such as negative and positive repelled one another. And so he hypothesized that that beam was negatively charged, and he called these particles corpuscles, and we later called them electrons. Now, why did he think they were negatively charged? If you actually look back here, remember, opposites attract. So since it was attracted to the positive, this had to be a negative. It was also repelled by the negative, so two negatives repel one another. So it's a pretty good experiment. Here is an actual real-life setup of a cathode ray experiment. And again, here he has hooked it up to an electricity source. He's passing a ray through it. And even when he puts a magnet up here, because magnets have different poles that are positive and negative ends, it even causes the ray to be deflected. And so he concluded that electrons are in all atoms. So he said all atoms contain electrons. Now, electrons were further built upon by another scientist. He was a U.S. physicist. His name was Robert A. Millikan, and he wanted to find out the quantity of the electron's charge. Not just that it was negative, but what degree was it negative. So if you're looking at your test, what you should know that Robert Millikan did quantity of the electron's charge. And he did this, and you should know that his experiment is the oil drop experiment. So what he did was he took these negatively charged oil droplets, and he suspended them and dropped them between two charged plates. And what he did is he changed the voltage, or how much electricity he was giving the plates, to see if the drops fell faster or if the drops fell slower. So from his data, he actually found the exact charge of an electron. And he found out that the electron's exact charge is 1.6 times 10 to the negative 19th coulombs. So here's a good picture setup of his experiment. Up here is a sprayer that gives out the oil droplets. We had electrically charged plates. So up here we had a positive plate. Down here we had a negative plate. And then he gave in sources of X-rays and different voltages. So he changed it to see how fast did they fall through this. And he viewed it through the viewing microscope. So using this charge and Thompson's charge to mass ratio of the electron, Millikan was able to actually figure out the electron's mass. So that's another thing that Millikan did. He found the electron's mass. And Millikan's values for the charge and the mass are actually really similar to what we accept today. So he did a fantastic job in his experiment, considering that it was carried out and he lived between 1868 and 1953, when there wasn't near as much technology as there is today. So we say, based on that, he found out that the electron's mass is 1 divided by 1,840 mass of a hydrogen atom. So it is extremely small / light. In fact, you're going to find out that the electron has a smaller mass than both a proton and a neutron. So let's go on and talk about some protons and neutrons. If a cathode rays are electrons given off by atoms, well, then what is actually left behind in the atoms if it loses those electrons? So basically, someone posed the question, if a hydrogen atom loses an electron, what's left? What's left that still makes it an atom? Now, you can think through this problem or this question using 4 simple ideas of what we know about matter and what we know about electric charges. The first idea is that we know that atoms have no net electric charge. It means they are neutral. It does not have a positive charge. It does not have a negative charge. So this is a very important concept. If you don't have it written down or highlighted, I would highlight it. 2, electric charges can be carried by particles of matter. So if it loses a negative charge, we know that there's usually a charge left. We also know that electric charges exist as whole number multiples, and there's no fraction of a charge. So you can't have half of a negative charge or 2.5 of a negative charge. It has to be a -1 or a -2. And then number 4, when given number of negatively charged particle combines with an equal number of positively charged, that is how we get an electrically neutral particle. So if you have 2 negative and 2 positive, well, -2 plus 2 gives you 0. It's neutral. So if you think of those 4 things that we know, it follows that the particle with 1 unit of positive charge should remain if you lose an electron. So what's left behind are a positive charge, and we call those protons. In fact, in 1886, Eugen Goldstein, when he observed the cathode ray tube experiment, he found that rays traveling in the direction opposite to that of the cathode ray. And he was the one, he discovered protons based on J.J. Thompson experiment. And he said, hey, these are positive particles, and we're going to call them protons. So if you were to define protons, they are positively charged subatomic particles. And then last but not least, we have to cover neutrons. So in 1932, an English physicist named James Chadwick, he confirmed the existence of a neutron. So if you're matching up scientists for your test, Chadwick discovered neutrons. If you don't know what a neutron is, it's a subatomic particle that has no charge, so it's not positive or negative, and its mass, how much there is equal to a proton. So protons and neutrons' mass are the same, and electrons are smaller than both protons and neutrons. So over here is kind of a table that summarizes what we kind of know about electrons, protons, and neutrons. If we're talking about electron, its symbol is E with a negative, so E stands for electron. The negative stands for it gets a negative charge. P, proton, with a positive charge, because it's positively charged. And the neutron is the letter N with the 0, saying that it has no charge. So its relative charge is negative, positive, and no charge. And then in terms of its mass, protons and neutrons are equal, and then the electron is extremely smaller or tinier. But when you look at the actual mass, again, the actual mass here, they're the same for protons and neutrons, and electrons, of course, is smaller. So although protons and neutrons are extremely small, theoretical physicists actually believe that there are even smaller particles or subnuclear particles known as quarks. That leaves with the checkpoint question. What evidence did Thompson have that led him to conclude the cathode ray was a stream of negatively charged particles? So pause this video and see what you come up with. If you look at the evidence, hopefully you stated that the beam, one of the evidence, the beam was attracted to positive plate and repelled by negative plate. So opposites attract. So if it's attracted to positive, it had to be negative, and like charges repel. So if it was repelled by the negative, that means the stream also has to be negative again. So that's the end of today's lesson. If you were confused on anything, please make sure that you're asking questions, and I hope you have a great day.